Hello, this is Catherine Davy. This presentation is about the trapping efficiency of Portland-based mortars incorporating a hydrogen and tritium getter. This research is performed in collaboration with CEA Marcoule. It is funded by PIA2 as the MAC3 project. So the industrial context is the ITER facility. It's an international project aiming to develop a nuclear reactor based on fusion to provide energy more than current nuclear reactors. So this ITER facility, when it will start to operate from 2020 normally, will generate the largest amounts of tritiated waste in gaseous and liquid forms. Although the half-life of tritium is relatively short, it has to be handled. And so these waste are currently planned to be conditioned by cementation, that is to say immobilized in containers made of a cement-based binder. The issue is that gaseous tritium may accumulate inside the containers. Its pressure will increase, and at some point, the tensile resistance of the cement-based binder may be reached so as to crack the container, and tritium may leak in the environment. So we want absolutely to avoid that. So what is currently feasible is the following. It's an international patent designed by D. Lambertin and C. Codicum and co-authors, which is cement pastes, and particularly a Portland cement paste, including a hydrogen getter, which is a mix of manganese dioxide and silver dioxide. This getter has shown its efficiency when it's incorporated as a powder in a Portland cement paste, which is cured in wet conditions for 14 days at 32 degrees, but after drying at 60 degrees for 48 hours. And this step of drying at 60 degrees for 48 hours, which is necessary to use this cement paste as the patent proposes, is not realistic at the industrial scale. So the aim of our project, which I present today, is to develop another Portland cement-based material, rather a mortar, still on this same MnO2 plus Ag2O getter, but without requiring drying. So how is this possible? When you go back to this MnO2 plus Ag2O getter, first it has been shown in the literature that it's efficient both for hydrogen, as in the patent, and for tritium, tritium trapping. And the discovery by Kozawa in 1981 shows that it's also efficient in the wet state. So our objective is to propose a mortar to immobilize the tritiated waste, as you can see here. And the tritium as a gas can flow through, will have to be able to flow through the pore system of the mortar, which will have to be emptied of water. And the presence of the getter, figured here, will allow to trap the gaseous tritium. So we have chosen to use either pure Portland cement, CEM1 cement, or composed CEM5 cement. We incorporate the getter as a powder or as porous granules to increase the pore volume. And we will have also a control over the general gas permeability of the mortar to limit the flow rate of tritium gas to allow allow the getter enough time to trap gaseous tritium. And no drying has to be necessary for this mortar. So the methodology followed to design a Portland cement-based trapping mortar has been to slightly change the sand grain skeleton of the mortars, to incorporate the getter as powder of granules. During the formulation, we used an analog to the getter, which is the MnO2, which is cheaper. So this formulation has been performed according to the industrial specification, and we only retained the mortars compliant with this specification. And today you will see the assessment of the durability of these mortars, but only on the point of view of the interaction between the cement and the getter, and the hydrogen trapping efficiency of the mortars through gamma ray irradiation tests. So the mortars developed are based on a normalized cement paste made with a water to cement ratio of 0.5 and with a normalized sand granulometry. We have been selecting two sand classes, the biggest and the smallest, the biggest here and the smallest here, added with the getter as a powder, and we obtain a ternary water to cement ratio of 0.48 mortar. Here, it's our first mortar, a ternary mortar, which is made with big sand, small sand, and getter and cement paste. We have another ternary mortar which is more suited to CM5 cement with a water to cement ratio of 0.54. And we have a quaternary mortar with CM5 cement, which uses getter granules in complement to getter powder. So as you can see here, the capacity of the reference mortar is 68%, the capacity of its sand skeleton. When we select only the two sand classes, we are decreasing the capacity. When we use MnO2 powder, we significantly increase the capacity, which is not very favorable to have a porous system accessible to gaseous tritium. So with the quaternary sand skeleton, we go back to a capacity which is equivalent to the reference mortar. So in terms of interaction between the getter and the Portland cement, by qualitative XRD after about 4 months curing in endogenous conditions of cement pastes, we found no new crystalline phases due to the presence either of MnO2 or MnO2 and Ag2O. With mass NMR, silicium, and aluminium spectra, we also found no significant differences in the structure of the CaSH hydrates in presence of MnO2 or getter. We have possibly a less mature paste in presence of MnO2 or getter when it's added in supplement to the pure paste. So the trapping efficiency is measured with a gamma irradiation experiment on a Gammatech facility located in the south of France. It displays a cobalt-60 gamma ray source, which can irradiate the mortar cured for 3 months in a hermetic tubes before irradiation. The irradiation is of either about 500 or 1000 kilograms, which corresponds to 23 to 46 days irradiation, which is quite long, but it's sufficient to have a detectable hydrogen production detected by gas microchromatography. We detect H2, but also other gases, but the results show that we only have H2. We have no other gas present after the irradiation. And why do we use gamma ray irradiation? Because the ionizing ray allow water radiolysis and generate hydrogen gas in situ, which means inside the mortar. So the raw hydrogen production results are presented here in micromole hydrogen per gram water. So the results on the monolithic mortar samples are compared to the hydrogen released of pure water subjected to the same irradiation for the same quantity of water present in the mortar, with about 500 kilograms for the 3 mortar formulations designed in this study. We have here for pure water a bit more than 20 micromole per gram water here, but the results in black. With 1000 kilograms, we have again results in black, more than 40 micromole per gram water. But when you compare to the mortar added with getter here, the three formulations at 500 and here at 1000 kilogray irradiation, we have a significantly smaller hydrogen production. So we determine from these raw results a trapping efficiency parameter, which is the difference between the hydrogen produced by pure water minus the hydrogen produced by the mortars added with getter, divided by the hydrogen produced by pure water expressed in percentage. And you can see that the trapping efficiency is between 76% here and 95% here, depending on the mortar formulation. So here you have the ternary mortar based on CM1, ternary mortar based on CM5, and quaternary mortar based on CM5. So the best trapping mortar is the quaternary one, as you can see here, with more than 90% trapping efficiency. So as a conclusion, we developed mortar based on Portland cements and incorporating this MnO2 plus Ag2O getter, which significantly traps hydrogen in situ. The interactions between the cement and the getter are negligible, as shown by XRD and mass NMR. So further, we want to analyze whether this also works with tritium, with actual tritium, which is what's coming next in this project. Thanks for your attention.